Hi everyone, welcome back to our channel, Becoming a ROS Developer here at The Construct. My name is Rodrigo, and today we're going to be doing a project presentation for one of our courses. This course is ROS 2 Basics, in 5 days in Python. And our student Daniel is going to show us what he has done with the project and just explain us how he did it. So, hi Dan, how are you?
Hi, great, thanks.
Yes, so like I said, whenever you're ready, you can start showing us what you've done. You can share your screen and just start your presentation.
Great. I'll start sharing now. Okay, so starting off, I'll share the view of the robot.
Okay, yeah, I can
Hopefully,
see it.
that works. And the robot's currently in the starting position. I will open up my shell and launch the node.
And while it's doing things, you can just kind of like mention what it's doing.
So currently, it's running the find wall service, which locates the nearest obstacle, rotates the Turtlebot to face the obstacle, approaches the obstacle within 0.2 of a meter, then performs a 90-degree anti-clockwise turn to assume a starting position. Once that's done, it begins to follow the wall on the right-hand side. And whilst it's doing this, it's also running an action client, which is recording the odometry of the robot as it moves around the course. The odometry is stored in a variable within the action server, and at the end of the route, or once it's performed a single lap, then it's going to be printed to the console, which I'll bring up once the lap's been completed.
Mm-hmm. Well, perfectly explained. That's exactly what I wanted. So how do you determine that it's a one lap?
So what I have set the action client up to do is to evaluate against a goal condition. The goal in this case is to approach within 0.5 of a meter of the initial starting position.
Oh, that's
In
great.
this case, it's the position that the Turtlebot's in when it begins to follow the wall on the right-hand side.
Okay, we'll look at how you actually did that later.
So there we go. The action client has returned. We've performed a full lap.
Uh-huh.
As the action client was going through, it's been posting feedback, telling you the total distance traveled by the Turtlebot. And then as it reaches its goal, it prints a history of all the odometry points
Okay.
that it's moved through during the execution of the action.
Right. Okay. And I see it's still moving, and it'll continue to do this forever. Like it'll do the lap and then return it, and do the lap and then return it.
It will. So the action runs for one lap only. Once I cancel the node,
Okay.
the motion will stop.
Oh, all right. Okay. Cool. All right. Well, very clear. So could we now like take a look at how you did each section, just so we can see how you did the service server, the main program, and
Absolutely.
the action server?
Let me bring up my slide deck.
Just so you know, you stopped sharing your screen.
Yeah, I'm going to be sharing a different screen here.
Okay.
There we are. Hopefully you can see that now.
Yes, I can see your presentation now.
Okay, so as an introduction, obviously this is the wall follower task from the ROS Basics in Python. The task demonstrates the use of publishers and subscribers within ROS. It demonstrates services and service clients, and action servers and action clients. The first task is a simple publisher and subscriber. This is what dictates the behavior of the wall following programming. What that involves is subscribing to the data coming from the laser scanner and publishing to the CMD-vel topic, which the Turtlebot subscribes to, which controls the velocity of the robot. So the laser callback saves data to the node's properties so that they can be accessed later by other methods of the node, and that allows the Turtlebot to access the location, or to monitor its environment, as it were, as it moves around the course. So after defining and instantiating the subscriber, I also define a publisher, which publishes to the CMD vel topic, which, as I said before, controls the velocity of the robot. And effectively, I use the update velocity function, which there's a screenshot of there, to dictate the logic of the wall following behavior. In this case, I did it hierarchically. The first check that is made is to check for an obstacle in front of the robot. If there's anything within 0.5 of a meter of the front of the robot, then it slows down and begins an anti-clockwise turn to turn a corner. The next check is to evaluate obstacles on the right of the Turtlebot. If the Turtlebot's too close to the wall, it'll begin an anti-clockwise turn away from the wall. If it's too far away from the wall, then it'll start a clockwise turn, and so on. Failing all of those, or rather passing all of those, it will speed back up and cancel any rotational velocity to continue following the wall. Okay. And that's the wall following behavior, which is fairly simple and was just a combination of publishers and subscribers. The next task, which is what the Turtlebot actually performed first in the demonstration, is the wall finder service. Now, the service server, it runs as a node on the ROS network and can be called by a node within the network to provide a service effectively. And in this case, the service is that the Turtlebot will locate the nearest wall, move towards it, and then set itself up in position to follow the wall, to continue the wall following behavior. So the first thing that involved was defining a custom, The first thing that involved was defining a custom service. In this case, an empty request is received by the server, and then once the service has been performed, then it returns a Boolean true or false statement on whether a wall's been found. So this service server listens for these find wall requests, find wall being the custom service file, but it also requires a subscriber. Again, we're going to subscribe to the laser scanner topic so that we can monitor obstacles around us, but this time we're doing something different. Because we're finding the closest object, we need to find the minimum of the points returned by the laser scanner and also record the position that minimum distance is recorded in. Now, the laser scanner has 2 positions per degree in the 360 degrees that are scanned, and so a basic calculation gives you the angle that the Turtlebot needs to rotate through to face the closest obstacle. So that's done on the laser callback. Those basic calculations are done on the laser's callback. We also define a publisher again to the CMD vel topic because we're going to do some maneuvering as well. Now, the wall finder logic, as I just hinted, is effectively calculating the angle required to turn the Turtlebot through, and then calculating how long the Turtlebot needs to move for at a given angular velocity. So the node publishes commands to the Turtlebot, telling it to rotate for a specific time as calculated by how long is necessary to perform the maneuver.
Right. So by time, you get the time and then you rotate for that amount of time.
Correct, yes. So I calculate the radians it needs to turn through, divide that by the angular velocity that I've set the Turtlebot to move at, and then send that message for that amount of time. After which I send a stop message to the Turtlebot, which cancels all the velocity, at which point it should have completed the rotation.
Right.
Okay. Similarly, there are two further maneuvers. The next maneuver after the initial rotation is to approach the wall, which is fairly simple. It's again done through a calculation of the time required to perform the maneuver. Calculate the distance, divide it by the velocity that the Turtlebot's going to move at, and that gives the time that the maneuver is published to the robot for. Once the wall's been approached, send a final message to cancel the velocity and move on to the next maneuver, which very similarly to the first maneuver is a rotation.
Rotate 90, okay.
and it's to rotate 90 degrees so that it's parallel to the wall on its right-hand side. Once the maneuvers are all complete, then we return a Boolean statement, in this case, success, that a wall's been found, and we know that the robot's ready to continue on its path. The final task was to create an action server and an action client. The action server is to record the odometry of the Turtlebot as it proceeds around its path. Once it's completed a lap of the circuit, then it will return a list of all the points that it has moved through in the odometry throughout the execution of the action. In this task, we are introduced to the concept of multi-threaded executors in ROS, which allows us to execute multiple tasks simultaneously as the robot proceeds. And I'll explain more in a little bit. So similarly to a service, we define a custom action here. In this case, actions have three things that you need to define. You have the request, which in this case is empty. You have feedback, which is provided throughout the execution of the action, which differentiates it from a service. And then you also have the result. So in our case, the feedback is just a constant return of the total distance traveled, effectively an evolving update of how far the Turtlebot has moved around the track. And then the result, which is a list of all the odometry points that the Turtlebot's moved through over the course of the lap. Now, callback groups, I use two for this action server. One I use for the subscriber, which is constantly receiving information from the odometer, and one I use for the action itself. This is so that the action, whilst it's executing, can access data that retrieved by the subscriber whilst during execution, so that one does not block the other. And that's important to this.
Right.
So yeah, like I say, two callback groups. The first one is the odometer subscriber, and the second is the action group. Now, when the action is requested by a node on the ROS network, the action begins to execute. It's received a goal and a few things we've got to set up first. So the first thing that happens is I instantiate a list to contain all of the odometry messages that are received during the execution, and reset the variable for the total distance traveled, as we're only recording it during the execution of the action. We also initialize the feedback message. If you're looking at the code on the screen, you'll also notice I've got a flag variable called first time.
The first time one.
Yeah, I'll come to that now, because the main loop of this action is a goal check. This goal check is evaluated throughout the execution of the action, and effectively this monitors whether we've achieved the goal of moving within 0.5 of a meter of the starting position or not. And that's why I've got this flag variable, because on the first time of execution, we know the Turtlebot hasn't moved, and so we can ignore the evaluation of the goal. Similarly, there's additional logic in there to prevent it being returned as true too early, because the Turtlebot needs to move away from the initial position before it can be considered as having achieved the goal. So there's an arbitrary distance minimum distance imposed on the goal check first.
Right, so it doesn't stop right away. Is that correct?
Correct.
Because it would be too close. Okay, yeah, I understand.
Yeah. So the goal is evaluated by calculating the scalar distance between the first odometry point that is recorded at the point of execution, and the latest odometry point that's received. So you're constantly comparing your current position with the very first position recorded until that scalar distance is 0.5 of a meter or less. And this is the rest of the main loop. So the goal check is evaluated in a while loop, and several things happen within that while loop. We've got the extraction of the X and Y coordinates from the odometry message, which contains a lot of other data that might be useful for other applications.
Hmm.
But for us, we are only interested in the X and Y coordinates, which we extract as a point, which is a message format within ROS.
Mm-hmm.
With that extracted point, we calculate the scalar distance between the latest odometry message and the one previous, and we use that value to increment the total distance traveled by the Turtlebot. We then publish this total distance traveled as feedback, as a feedback message, so that the action client is receiving feedback throughout the execution of the action. And we iterate. It goes back to the evaluation of the goal check, and it goes until the goal is achieved.
Right.
Once the goal is achieved, we flag the action as a success, and we return the history of odometry that we've been saving throughout the execution of the action.
Okay.
And
That
that's it.
returns.
Yeah. The final thing was to tie all of this together. So effectively incorporating the clients for the service and the action into the wall following program, and adding all of those nodes, adding the servers of those actions and services to the launch file.
The launch file.
Yeah. So again, I used multiple callback groups for this, so that the nodes could run in a multi-threaded way. And with the service client, with the finding the wall, that runs in a blocking manner, so that nothing happens until the wall has been found and a suitable starting position has been achieved. Whereas the action server, or the action client, should I say, runs in a non-blocking manner, because we want that odometry to run whilst the wall following logic is being executed.
Yeah.
And that's it. Adding the nodes to the launch file, we can then launch the entire thing with one command.
Hmm.
And that's everything.
Awesome. Well, I got some questions. Congratulations, first of all. And do you mind stopping sharing your screen so we can?
Yeah, absolutely.
Because I don't have like specific questions about the code, but I mean, congratulations. Really nice, really clear explanation, really sectioned and uh, perfectly perfect way to understand it. So
Thank
I
you.
really liked, for example, the goal checking function method that you did for the action. I think that's really useful. That flag, for example, that you'll find that something like that is really useful for like 80% of robot applications. You could do something like that. So
Yeah.
I think that's really nice, especially for example, you have a timer callback, you have a timer function, and you want to be checking things in that
Yeah.
timer and do things like you'll find it's pretty much that. So I really like that. And you mentioned something at the end, because at the beginning I thought, he probably doesn't know that he can do a mutually exclusive callback groups in the service server. But then you talked about how the service server works in a blocking manner, because
Yeah.
of course it doesn't actually need so once you execute the service callback, you don't need to then be subscribed to the scan, which executes another callback, and then that's how you perform the movement. I think that's really clever, and that would be the solution, the only available solution in Python and I think C++, if you didn't have something like this. So my question, I guess, is, did you do the service server before learning about the callback groups, or is it because in the instructions you were instructed to do that until after?
Yeah. So when I started the course, there wasn't yet a section
A
on
section,
callback groups.
right.
I did look into doing it through using callback groups, and the solution to doing the find wall service would be fairly self-explanatory if you had mutually exclusive callback groups. But since the Turtlebot isn't in a dynamic environment and everything is static except the Turtlebot, then you can sort of
assume
run
that.
it in a blocking manner and assume that nothing changes other than what you are causing to change through direct execution. So yeah, it's effectively just storing the necessary variables and acting on them with the assumption that they don't change. Obviously, in a more dynamic environment, you would look to have separate callback groups so that you
Right,
can
to maybe
constantly
stop.
monitor the environment.
Yeah,
Yeah.
but I really like how this was presented, because I could see, you can then see the necessity of a
Yeah.
callback group to avoid blocking, two callbacks. Just one thing I wanted to mention,
Hmm.
you added, you did two groups for the callbacks, for one each callback. You can just do one group, right?
Yes.
So you can do the mutually exclusive callback group for one, and I don't know how many you can put in. I have never tried, but at least four it works. But I mean,
Yeah.
that's just a detail. The
Yeah.
important part is that you understood why we have to do that
Hmm.
execution. And also, I think it perfectly exemplifies the differences between a service server and an action server. Basically, in a service server, you will have a program block, let's say, until that service is returns a result. And for
Yeah.
an action server, you can do other things like what you did with the odometry. So
Yeah.
uh, it's sort of like the action server allows you to do other things while you expect for that goal return. And this is another important point that I think you understood clearly. And
Great.
I mean, other than that, I those are all my comments. It was a really, really nice and clean project, and yeah, congratulations
Thanks.
again.
Yeah. Thank you. It's been good fun.
All right, I'm glad to I'm glad to hear that, and I hope it helps you to, expand it to, and you can kind of put in your mind what you need to do to keep improving and adding
Yeah.
functionalities and things like that, which is the goal for a course like
Yeah.
this.
It's definitely going to stand me in good stead for a couple of projects that we're doing and working on. We're hoping to use ROS to control the robot or the cobot that we're putting in part of our manufacturing cell. So
Oh, nice, nice. Is it a manipulator arm or a?
yeah, it's going to be pick and place to begin with, but we're adding a vision system to it and all sorts of peripheral sensing to do other things
Oh,
as well.
nice. That sounds interesting. Well, we got some courses for that. We don't have a real robot project yet, although we're working on that. So I
Great.
hope that they're useful to you as well.
Yep, I'm sure they will be.
All right. Well, again, thank you, Dan, for your presentation. Really nice. And to whoever else that's watching, this is what you can do after you take our course and want to present your project to get a certificate. It's the final step, we say, in solidifying a learning experience online. So you can do what Daniel did here. And Daniel, again, congratulations and very well done.
Thank you.
All right, guys. Bye bye, everyone, and we'll see you in the next video. All right, awesome.